All right, so we're picking up from here. I have this equation. So the whole reason of wanting to have, multiplying by -1 so that we could flip over this fraction is that I could break this out as 1,000 over p minus 1, right? Because I can separate the minus sign in the numerator, which if the minus sign in the denominator, I wouldn't be able to do, equals e to the negative 0.0003t. And do I want to... Yeah, so then I'm going to go ahead and break off this e to the negative c. I say I, but again, I'm just copying the book. And then once we're here, we can say, all right, I know that r of 0 equals 61. This says they started with 61 moose. So this is, in fact, our initial condition. And it's truly an initial condition in the sense that the independent variable is time. The time is 0. So this is the number of moose when they started the experiment. All right, so then I can basically use this information to solve for the c up here. So I would say this is r of 0, so that is 61 is actually, I put r of 0, which is weird because it's actually p of 0, and I don't know where I got the r from. P is the population of the moose, okay? So since p of 0 is 61, that means I can put 61 for the p right there. So 1,000 over 61 minus 1 equals e to the negative 0.0003 times 0. And I could, of course, skip writing that because it's just 1, e to the negative c. So the result of that is that e to the negative c equals whatever this is, and I put that in my calculator, and it was 15.393. Same thing the book got. How about that? All right, now, so notice one thing that we did here is we didn't bother to solve for c itself. We just have this e to the negative c. We could call this a different value. We could call it k or something, right? Or r, whatever. We could call it a different variable. So that way, that's, but in this case, the e to the negative c, we just solve for it as it is. So now I can plug it into this equation, and then I will have from here 1,000 over p minus 1 equals e to the negative 0.0003t times 15.393, because that is what my value of e to the negative c is, right? Subbing for the e to the negative c, this 15, this 1 point, what is that? 15 point, I don't know where that extra stray mark comes from, 15.393. All right, so where do I go from there is an excellent question. Yeah, okay, I'll turn my page over and end up with 1,000 over p equals 15.393 e to the negative point. That's interesting. Why do I have negative 0.3 instead of 0.0003? Oh, because we actually changed it to 0.3, didn't we? We changed that way back here. So then everything that follows that is wrong. All right. So in our next video, we're going to go back and correct everything from... See, where's the point where we multiply by 1,000? Right here. All right. Lovely. So right here, where we multiplied everything by 1,000, this should have been 0.3t, because we multiplied it by 1,000. Maybe some of you guys caught that. This is 0.3t all the way through. Instead of redoing the entire video, I'll just say we don't really have 0.0003. We have negative 0.3t. This is 0.3t. This is 0.3t. So that when we get back over here, geez, this is 0.3t. This is 0.3t. This is 0.3 times 0, although it doesn't matter. This is 0.3t. So it is, in fact, e to the negative 0.3t. Yeah, that's what we get for missing zeros back at the beginning of the problem. All right, so now what do we have then? Oh, so now we can just, there's a really nifty, useful algebraic property that comes up a lot, especially in trig problems. If I have a fraction equal to a constant, you can switch the constant in the denominator. Yeah. Essentially, you're multiplying by b and dividing by c on both sides of the equation. So I always think of it like we can always just switch the number in the denominator. 1,000 over 15.393. Where'd my plus 1 go? Plus 1 here because minus 1 here, plus 1 there. All right. E to the negative 0.3t plus 1 equals p. And there you go. I finally got a function solved for p of t that is the solution to, this is the particular solution to that differential equation. Okay, now, you do not have to do all that every single time you encounter one of these problems. In fact, in general, when dp dt equals kp m minus p, then you have a logistic equation or a logistic function, and the result you're going to have is p equals m over 1 plus a e to the negative mkt. All right? Now, the a is a constant you are generally going to have to solve for. So this is sort of like a version of c. It's a version of c that you have to solve for using an initial condition. All right, and but you don't have to do all this because you're going to know that once I have a logistic equation, because this is my differential equation, this is the equation that's going to handle that. That, in fact, is laid out for you in your book on page 367 at the bottom. It's the general logistic formula. Yeah, so that is chapter 6, page 367. You can look at this crucial solution. And then basically, we can use this to solve any logistic problems when the logistic problem might be phrased to us in this way, and then we'll just know that this is the equation to use. And then we can, solve for the unknown variables and solve any problem around it in the same, using algebra in the same way that we did for the exponential equation. We will look at doing some examples of that next.